Question 21 is strange because the solution can be gotten easily without really knowing what's going on in the problem. It's a tale of two CFMs, both of which make up one single airstream. It tests your ability to distinguish using CFM in so-called standard circumstances from CFM being used to determine mass flow. Finally, it demonstrates, through a heat gain calculation, the greater importance of mass to energy over volume to energy. Initial critical thought solution elements. 1. What are you solving for? The heat gain required for outside air entering a conditioned room. 2. What is the fundamental process? Sensible heat gain. 3. What are the first considerations to find the solution in connection to the fundamental process? Determining what air is standard, and what to do with the densities provided in the question. 4. Are there key assumptions? Sea level altitude, steady flow energy transfer, and the possibility of useless data given. From the information provided in the question, the fundamental setup looks like this. You're solving for heat gain, but the question doesn't say which heat gain. Total? Sensible? Latent? Look for the variables used in these three standard air heat gain equations. Dry bulb temperatures are given, so that indicates solving for sensible heat gain. With changes in dry bulb temperatures, the calculation is definitely not for latent heat. But dry bulb temperatures aren't the only thing given. You're also given densities. The inverse of density is volume. So you have dry bulb temperatures and volumes for the air. With these two variables, look on a psychrometric chart and determine the enthalpy of the air. Maybe you're solving for total heat gain. Are you solving for total heat gain or for sensible heat gain? There's no further evidence in the question to tell you which. You have to make an assumption. To solve for total heat gain, find the enthalpies of the room air and the outside air on a sea level psychrometric chart. At 50 degrees dry bulb and 0.077, the volume is 12.987. The intersection of 50 degrees dry bulb and 12.987 is an enthalpy of roughly 19.7 BTU per pound. At 0 degrees and 0.086, the volume is 11.6279. The intersection of 0 degrees dry bulb and 11.6279 is an enthalpy of, oh wait, that doesn't exist. So therefore you must be solving for sensible heat gain. The sensible heat gain equation for standard air is this. But is the question using standard air? What makes this equation assume that the air is standard is found here, in the 1.1. Find the fully exploded heat gain equation in the NCEES Mechanical Reference Handbook, section 9.1.7. The 1.1 is made up of a time conversion, density, specific heat, and humidity ratio. Time has nothing to do with air being standard. Specific heat for dry air is only one value. Same goes for specific heat of water vapor. So that leaves the density and humidity ratio. Focus on density. As the air changes temperatures, it changes densities. And the change can be quite large. Let that sink in. Standard conditions for air is directly connected with an assumed density and assumed temperature. Look up in the NCEES Mechanical Reference Handbook on page 4 to see that standard air has an assumed density of 0.075 and temperature of 69 degrees Fahrenheit, and obviously a sea level altitude. Notice density is given in this problem. This indicates that the air should not be considered standard. A word about this humidity ratio. According to ASHRAE Fundamentals, Chapter 18, Equation 8, a humidity ratio of 0.01 approximates conditions found in many air conditioning problems. The NCEES solution assumes a humidity ratio of 0. But from the psychrometric chart at the intersection of 50 degrees dry bulb and 12.987 volume, the humidity ratio is roughly 0.0068. When doing calculations in the PE exam, you're solving for most nearly values, and the difference between 0 or 0.01 or 0.0068 will likely not affect the outcome significantly enough to take you far from the desired solution value. Now to apply the values in this equation to find the correct solution. This video is brought to you by ExOverZero, which offers the best PE study tools possible. To purchase our practice exams, use the link below. The delta T is 50 minus 0, the two dry bulb temperatures. The question gives 21,000 CFM here. But that's not the air that's being heated. That's the air that's being exhausted. And you're supposed to solve for the air that's being heated. Isn't it the same, though? What goes out must come in, right? Well, cold air is coming in and being heated, and the density's changing. The reciprocal of density is volume, so the volume is changing as the air is being heated. CFM is a volumetric measurement. So a different CFM is flowing in than the CFM flowing out. What doesn't change is mass. Mass balance is critical, and no mass was created in the room. This 21,000 CFM is the room air at a density of 0.077 flowing out. So this mass flow is 1,617. That must be the mass flow of what's flowing in. Using simple critical thought, just divide that 1,617 mass flow by the 0.086 density of the air flowing in, and get 18,802.3. 2 CFMs for one airstream. Using ASHRAE's assumed humidity ratio of 0.01, all the variables are set. Heat gain equals 60 minutes times 0.086 times 0.24 plus 0.45 times 0.01 times 18,802.3 CFM times 50 minus 0, equaling 1,186,068 BTU per hour. Option C. Notice that you could have just blindly put 21,000 CFM into the standard air sensible heat equation and got 1,155,000 BTU per hour. This is closest to option C of all the multiple choice answers. Just because you may have done that in your practice doesn't mean you know what's going on in this problem. It's more of a lucky guess. So to get good at questions like this, study ASHRAE Fundamentals, Chapter 18, sections titled Standard Air Volumes and Heat Gain Calculations Using Standard Air Values. In the ExOverZero practice tests, do problems Test 1, 23, Test 2, 22, Test 3, 21, and Test 4, 21.